Now that we've done tangents and areas under curves, the next thing that we will look at is arc length. So once again, recall that the arc length L between A and B for a curve would be given by square root of 1 plus dy over dx squared dx. And once again, the question is, what about in parametric form? What about in parametric form? So for this, we have a theorem. So if a curve C is defined by parametric equations given by x is f of t, y is g of t, and we have that t is between two values alpha and beta, where f prime and g prime are continuous on this interval alpha beta. We need it to be continuous so that we can take the so that there's no there's no like infinite tangent things happening over here. And the curve C is traversed exactly once as t increases from alpha to beta. This condition is necessary because we're looking at arc length, and sometimes it's possible to have multiple loops, but in this case we just want it there to be one loop, otherwise it's gonna double count the arc length, right? Then the length of C is the parameters go from alpha to beta. We still have a square root, but we have a dx over dt squared and a dy over dt squared, and all of this integrated with respect to dt. Let's use this example to work with the unit circle, because we know what the arc length for a unit circle should be, right? So suppose we have x equals cosine t and y equals sine t, which recall is a unit circle. So what do we need here? We need dx over dt, which is negative sine t, and a dy over dt, which is cosine t. So the arc length going from 0 to 2 pi becomes square root of sine squared plus cosine squared, which is just 1. So it comes out to be 2 pi, which we know is, if we have a unit circle, the circumference is 2 pi. Right, so it works out fine. Let's look at another example. Suppose we want to find the length of one arc of the cycloid, again given by x is r theta minus sine theta, and y is r1 minus cosine theta. As before, one arc means that theta is varying from 0 to 2 pi. It also means that I'm going to need a dx over d theta, which is r1 minus cosine theta, and I'm going to need dy over d theta, which is, the first part becomes 0 because r is constant with respect to theta, and I just get r sine theta. The next thing I need, and I can do this calculation outside of the integral, is what happens if I square these things and add them, right? So I'll get an r squared a 1 minus cosine theta whole squared plus another r squared sine squared theta. Taking r squared common and foiling this out, 1 plus cosine squared theta minus 2 cosine theta plus sine squared theta, which is r squared. Cosine squared theta plus sine squared theta is 1. 1 plus 1 is 2. So I get 2 minus 2 cosine theta. So I have 2r squared 1 minus cosine theta. So what is my, let's go back to our integral. I can further write 1 minus cosine theta as 2 sine squared theta over 2. What is that from? That's from cosine 2 theta is 1 minus 2 sine squared theta. Right? So 1 minus cosine 2 theta is 2 sine squared theta. And here we have 1 minus cosine theta. So since I replaced 2 theta by theta, this means this theta will be replaced by theta over 2 because of the half relation. So all of this comes out to 4r squared sine squared theta over 2. Now, doing this separately means that when I plug this into the arc length formula, it's just square root of this term. 4r squared sine squared theta over 2 d theta. That's 0 to 2 pi. That's 2r sine theta over 2 d theta, which is 2r negative 2 cosine theta over 2, going from 0 to 2 pi to r. So cosine of pi is negative 1 times negative 2 is positive 2 minus cosine of 0 is 1 minus negative 2. So 2r times 4, which is 8r. So that's the arc length for the cycloid, one arc of a cycloid. So that's it for this particular video.